start this recording. Okay. New week. Let's do this. New chapter. Wow. Just flying through. So if you didn't get a formula sheet earlier, they're the same. There's only one hole punched one left. Then we're on to the non-hole punched ones, but they're the same, I promise. And they're the same as the one posted on Moodle. These are yours to study with, mark up, do whatever you need to do, right? And then I'll bring fresh copies to the test. So you can't use your own, of course. You have to use mine, but at least you'll know what you'll have, right? And so we did do some formulas in chapter 2. Nothing too crazy, right? But today we're starting probability in chapter 3, and so we have to talk about all these things. So I wanted you to have a physical copy as well. Okay. Probability. Oh boy. So chapter 3 is on probability, and I will confess it's my least favorite chapter, and usually I just want to get out of here. It's I don't like it. But we'll see what we can do. We don't go very deep into probability, luckily. Okay. And so what gets confusing though is we'll talk a lot about probabilities later, but this is the only chapter where it's called probability. So I kind of keep those separate. Once you're done the course, you'll know what I mean by that, but not until then. So not very helpful. So chapter 3, some probability. And of course, where do we need to start? Well, we need to start, yeah. Yes, but let me check. Yes, I'm sharing my screen. I'm not on mute. I'm recording. You got me nervous. Where do we need to start? With pretty much everything. Well, we need some terminology, and there are some core concepts in probability that we'll need to absorb and understand. And so especially, well, it all kind of feels overwhelming, but in this first section, there's a lot of concepts and terminology that we need to just introduce and see. And so here we go. One of the main things that I want you to remember, and I am pretty sure I would have said it last day as well, but a probability is a proportion. Okay? And so a probability is just a proportion, which is roughly a percentage. I say roughly because we have to multiply by 100, so technically it's not exactly the same, right? So for example, we could have something like a probability is 1 in 4, right? Which is the same as 0.25 or roughly 25%, right? We have to multiply by 100. Probabilities don't have to be fractions, but often they are, right? If we think about tossing a coin, right, the probability of flipping heads, 1 in 2, tails is 1 in 2. I know what you're thinking. Well, it could land on its side, and it does some small fraction of the time. We'll ignore that case, right? Otherwise, we go from this very simple example of flipping a coin to it being too complicated. Okay, so for flipping a coin, there's only 2 options, 2 outcomes. Okay, and so usually for probabilities, we are dealing with fractions. Right? They don't have to be fractions, And of course, you can just convert them to decimals, totally fine. But just recognizing that all these p's, we use them interchangeably. Find the percentage, find the probability, find the proportion. Those are all the same questions. And so here, we use these, I call them the 3Ps. These 3Ps interchangeably. A random process is anything where we know what outcomes could happen, but we don't know which particular outcome will happen. That's what makes it random, right? So a random process is things like flipping a coin, rolling a die, right? Rolling 2 dice. Wow, crazy. Drawing a card from a deck of cards, all these things, right? But we know what all the possible outcomes are. Okay? And so when we talk about probabilities, really what we're talking about is the probability of some random process or from some random process. Blah, blah, blah. I'm not sure I've ever read this example, so don't worry about it. iTunes, blah, blah, blah. There are some key facts about probabilities that I need you to absorb. The main one, I guess, that's a cliffhanger. But first, we need to introduce what's called probability notation. Okay? Probability notation looks like this. So when we write P of A, you might remember function notation F of X, right? So whenever you have a bracket like this, then you read it as up. Let's write a note here. Probability notation. That's good to have first. Looks like this. And you read it as P of A. How you interpret it is the probability of event A. Interpretation is the probability of event A. And so A is just a placeholder for any event. Right? And so typically what we do is if the event is kind of implied, right, or understood, then we can write something like P of T, right, which implies that I've flipped a coin and I'm talking about tails. Right, the probability of flipping a coin and it being tails, which is the probability of flipping tails. The most common events that we'll talk about is flipping a coin, of course. So we have heads, H, tails, T, right? Rolling a die, outcomes a 6-sided die. 1, 2, 3, 4, 5, 6. All right, that kind of thing. And so, and if it's not obvious, then I'll have to define it. Okay? But we have some of these kind of core random processes that we talk about all the time. So, what would you say the probability of flipping tails would be? Well, it's 1/2, right? 4.5. Huh? We'll dig deeper into why that is, but intuitively, right? You have two possible outcomes because we eliminated that standing on its edge outcome, right? It's too rare. Yeah? And so it has some probability, but we don't care. Yeah. And so right, so one out of those two outcomes has to happen. Yeah? But P of A is just a general notation that we use to denote any probability. Yeah? And so this is just a probability of event A, anything. Yeah? And for these events, we tend to use A, B, C, kind of beginning of the alphabet usually, if they're generic. Here's the fact that I kind of was building up to, and then I had to retreat because we hadn't introduced probability notation yet. But the most important thing that I need you to internalize about the probabilities, just as a fact, is that probabilities must be between 0 and 1. They're allowed to be 0 and they're allowed to be 1, right? But they have to be in between 0 and 1. So all probabilities must be between 0 and 1. And we have a good understanding of if the probability is 0, right, that means it'll never happen, right? The probability of rolling a die and it being 7, well, that's going to be 0, right? Because it'll never happen. How can it be 1? The probability is 1. It means it's always going to happen, right? No matter what. Well, we could say something like, well, what if I think about the probability of a heads or tails, right? I'm open to either one. The probability of one of those two, if I flip a coin, is going to happen. Well, it has to be 1, right? So those are your two extremes. But most of the time, probabilities are somewhere in between, right? 0.5 or 1 in 6 or something like that. I'm a frequentist. So there's two camps in statistics, and the Bayesians, they do their own thing, and it's relatively new. I mean, as new as computers are, because you need computers to be a Bayesian. But I'm a frequentist. You're a frequentist by default. And because otherwise we'd have to run all these simulations and stuff, and that's confusing. So for intro classes, we're all frequentists. So now you know. If you go to a statistics conference, someone asks you, hey, are you a frequentist or a Bayesian? And you can say, I'm a frequentist, but I want to be a Bayesian. Huh? That's pretty good. But that's for later courses. So what does a frequentist think? The differences are subtle, but the probability of an outcome is the proportion of times the outcome would occur if we observe the random process an infinite number of times. That's how we technically define probabilities. Okay? Effectively, what this becomes is you look at how many possible outcomes do I have, and we divide 1 by the number of possible outcomes. Okay? And so here, most of the time, we take 1 and divide by the number of possible outcomes. technically, when we say the probability of flipping tails is 0.5, technically what we're saying is, well, if I observed a coin flip an infinite number of times, I would expect half of them to be tails and half of them to be heads, right? But that also goes back to, well, because there are two possible outcomes, and I assume that they have an even probability, right? That's an assumption that we're making. And Bayesians are crazy. Fine, I'll tell you the basic idea. So a Bayesian goes the other way, and you need computers to do it, and just says, as a starting point, I'm going to say the probability of tails is 0.2. And then you run a bunch of simulations, and you make adjustments as you go until you land at 0.5. It's kind of weird. So yeah, we're not doing that. But the cool kids do that. Just forget it. Ugh. So in terms of probabilities, which of the following events would you be most surprised by? Now, the problem, maybe, is that all of these start with exactly 3 heads. Exactly 3 heads in 10 coin flips, I wouldn't consider strange at all. It's pretty normal. Exactly 3 heads in 100 coin flips, maybe now you're starting to wonder what's going on. Is this a weighted coin? Blah, blah, blah. But then, of course, the one you would be most surprised by should be because it's exactly 3 heads, right, in 1,000 coin flips. So just to get an idea of how things change depending on the number of trials that you have. The law of large numbers is everything is from probability is rooted in the law of large numbers, LLN. But it says that as more observations are collected, the proportion, right? But remember, the proportion is the probability, and it can be a percentage of occurrences with a particular outcome. Now we're introducing this p hat, which is really just a sample proportion. And it's got a subscript n, which you can ignore for now. P hat is a sample proportion. We don't need that until next chapter, I think. So, but it's nice to see it, and n will be the number of times we've done this thing. But it's going to converge to the probability of that outcome, which is p, which is going to be, so p is the population proportion. We've seen this kind of symmetry of a sample proportion or a sample something, a sample statistic, and a population parameter. And so for proportions, we have the same symmetry. Remember, for parameters, we tend to use Greek letters, mu, sigma, sigma squared, right? And so you could use pi if you wanted to, but pi is also a constant, right? A numerical constant. And so for that reason, I don't, right? But pi is a Greek p. So, but I will use p. So for proportions, that's really the only time that I use just a regular letter p. But we have the p hat to indicate that it's a sample proportion. So, what does the law of large numbers mean? Well, if I have something like this, and I have my p hats on the y-axis, and I have my number of times that I, let's say, flipped a coin. P hat of the number of heads, let's say. So this is the proportion of times that I get heads out of n trials, right? N flips. Now, at one flip, right, then maybe I'm still at 0. At 2 flips, maybe I have 1/2. 3 flips, and these are not, I'm not adding on to the flips, right? I'm starting the experiment over for each number of flips, which is kind of weird. And so what we get is usually what looks like something like this. And so as you increase the number of flips, right, what happens is this sample proportion tends to stabilize around the population proportion. Right? And so we kind of got at that with, okay, so a probability is how many times we would expect to see heads over an infinite number of tries, right? And so that's the law of large numbers. So there's a lot of variation. Right? Even when we said, okay, exactly 3 heads in 10 flips, that's lower than I would expect. How many do I expect? I expect 5 in 10 flips, right? But it's not that far off, right? So we would just be a little bit below the line, right? And so, right, depends on the number of flips, right? And so that's what we were getting at here, right? Exactly 3 heads in 100 coin flips. All of a sudden, you're expecting 50 heads, and you're only seeing 3. So that feels a little bit off, right? And it's because of the law of large numbers. Okay. That's not something I need you to know or anything. It's just trying to explain the background of probability. Okay. So if you're tossing a fair coin, if heads comes up on each of the first 10 tosses, what do you think the chance or the probability is that another head will come up on the next toss? Right? And so here, this is where you have to be really, really careful, because even though it looks like, oh, well, like this slot can't possibly be heads, right? This is what we call an independent event, right? It's an independent random process. So the coin doesn't care about what happened in the last 10 tosses, 100 tosses, right? It's just always 0.5. So the probability is still 0.5, because the coin is not due for a tail. This is what we call the gambler's fallacy, where you're at the casino. You're at the casino. No, but if you're gambling, and then it's going to happen this time, but usually these are independent events that you're talking about, right? And so flipping a coin, I don't think you flip coins at the casino, but that would be kind of funny. But what's that one, roulette with the ball and the disc? Put it all on red. That's the one. That should be independent as well, right? Assuming it's not weighted or anything, but right, that would be an independent event. And so, in terms of some notation, right, the probability of heads on the 11th toss should be the probability of tails on the 11th toss. So we can kind of explain the event if you need to explain it further inside the brackets, right? But you're still reading it as the probability of heads on the 11th toss is still 0.5, same as tails. And here I'll just clarify. We do introduce independence later, but I just I'll just write it here because it's nice to solidify it while we have it. Since tossing a coin yields independent events. Right. Each coin toss is independent of the previous and the next. A term that I think we tend to use in kind of everyday language is usually we say mutually exclusive, right? Or disjoint, right? Usually as an argument, those two things are mutually exclusive, right? What do you mean by that? Well, it means that they can never happen at the same time. Right? So in probability, we tend to use the term disjoint, but if you want to call it mutually exclusive, that's totally fine. I'll understand what you mean. But I tend to use the term disjoint. And so you can link those up if you want to, or just focus on disjoint. And so what it means is that we have two events that cannot happen at the same time, right? So if you flip a coin just once, right, it can't be both heads and tails. It has to be one of those, right? So kind of imagine them physically, I guess. They can never happen at the same time. Things like you cannot both fail and pass a class. It's one or the other, right? A single card from a deck can't be an ace and a queen, right? Whereas some non-disjoint outcomes, right? There are non-disjoint outcomes, means that two things can happen at the same time, right? We'll still be able to find the probability, but we have to be aware of if it's disjoint or not. Okay? So some non-disjoint outcomes, a student can get an A in stats and an A in econ in the same semester, totally reasonable, right? Those two things are allowed to overlap. What's another thing? A single card drawn from a deck can be a queen and red, right? There's some overlapping outcomes as well. So even in terms of a deck of cards, and I'll give you a rundown of kind of quick card terminology, but I don't put card questions on a test because I don't expect you to know cards, right? Card terminology. I flounder, so how can I expect you to? But on an assignment, you can Google it and kind of find out what it means. And so then I don't feel bad and I make you do card problems, but not on the test. Yeah. So, here is a full deck of cards. Here's some card facts. Some card facts. Well, there are 52 cards in a deck. Full deck is 52 cards. There are 4 suits. I think it's 4 suits, right? And I always want to call these clovers, but they're not clovers. Is it? Yeah. Okay. Help me out. Clubs and spades. Okay. But I'm not wrong in thinking they're clovers, right? Communication is communication. So we have 4 suits. So here, what did we say? These are clubs, spades, and then the hearts and the diamonds are kind of quick wins. So I'd try to stick with those. So those are your 4 suits, which means, well, we can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. I think I double counted one, but there's 13 cards in each suit. These guys are face cards because they have a face on them. And so there are 12 face cards. What else do we need to know about? That's probably it in terms of the numbers and things like that. Oh, and then these are jacks. Jack, queen, king. But besides the jack, I think queen and king should be kind of self-explanatory, and this is the ace, and all the others should be okay. Are there any others that can be confusing? Those are quick facts. As an example, what's the probability of drawing a jack? Well, I look at how many of those 52 outcomes are jacks, right? And so out of 52, I count 4 jacks, right? And so I have 4 out of 52, and that will be my probability of drawing a jack. Okay. A jack of hearts is a very specific card. In fact, it's 1 out of 52. And so you look at all the possible outcomes, which is 52, and to find the probability of a specific event, you figure out how many times does that event get satisfied in this deck of 52, and then divide by 52. But like I said, that's hard to do when you don't have this image, but this one might be nice to have. You can quickly Google it and find it for the assignments, because I know there are some card questions in there coming at you. Okay. So here we have some, oh, and I guess there's only 2 colors, red and black, but hopefully that's That's obvious, which means that there's 26 of each color. Of each color. Okay. Some of these outcomes, depending on the outcome, right, will be disjoint, and some of them won't be. And so if you want to talk about clubs and hearts, right, those are two disjoint events, right? If you're drawing one card from a deck of cards, you only get one of those, right? One of these four, right? Each with 1 in 4 probability, or 13 and 52. I know. But what I want you to be careful about is more the non-disjoint events. And you've seen it, we've already seen it in a table form, right? And if you've started on that assignment, there's the Tampa, Florida voters, which is particularly tricky. I want you to try it because the wording, the slight change in wording makes a difference. But today might help in kind of sorting that out. Maybe. Okay, so back to here. Here being this example. So I want to find the probability of drawing a jack or a red card. So I'm just drawing one deck or one card from a deck of cards, and I want to find the probability of a jack or red. I don't care which one, as long as it's one of those two. Yeah? So we can do the same thing. We can count up how many of those cards satisfy being either a jack or red, right? And so if you did that, what would you find? You would find, well, this is going to be 26 plus 1 plus 2, putting me at 28, which is what we have here. But we did a lot of kind of implied stuff, right? So if you don't have the deck of cards in front of you, right, usually you'll only have the probabilities. So what happens is, well, you might know the probability of drawing a jack. We already established is 4 in 52. And you know the probability of drawing a red, right, is 26 in 52. I'll do that up here. Probability of a red is 26 in 52. But if you were to just add those up, because either jack or red, I'm happy either way. In fact, whenever we say or will mean addition. And so or means addition. But if we just take the probability of a jack, that's this kind of green section, it's hard to see, plus the probability of a red, we're double counting the red jacks, right? And so really what we want to do is we want to subtract the overlap. So what we can have is the probability of a jack and red is 2 in 52. There are 2 red jacks in a deck of cards. And so here, what we need to do is the probability of a jack plus the probability of a red, which we've got printed nicely here, 4 over 52 plus 26 over 52, but then we have to subtract the overlap, right? Minus the probability of Jack and red. So we have to subtract the overlap. What's nice about these fractions and why I don't tend to simplify the fractions is because as long as I have a common denominator here, I can just add and subtract the numerators, right? 4 plus 26 minus 2 makes 28, which is the answer that we got to. But if we didn't have our deck of cards laid out for us, it would be hard to just see it, right? So we need some sort of formula to help us figure it out. Any questions? That's tricky. It's all tricky. I'll admit it. Before we do this, I'm going to just bring in our formula sheet because this is the reason I handed it out today. Just kind of press pause here for a second, I guess. Yeah, sorry.
What are the assignments and questions that would the answer that's up there be the final answer, or should we simplify it once we get the final one?
No, that should be fine. Yeah, so for the assignments, it should just accept it as 28 over 52 because it does math kind of internally. So it should just handle that. And for me, I don't need you to simplify on the test. You can convert it to a decimal because usually that's easier to read, right? And people kind of have an easier time with that, but you don't have to. So on your formula sheet, we have our general rules for probability models. Sounds fancy, but we've already seen one, right? The probability of A for any event A has to be between 0 and 1. That's the number one rule, right? And so if you try to tell me that the probability is 1.2 on the test, I'll say, no, it can't be. Right? But you should have a little internal check saying, oh no, that can't be, right? It has to be between 0 and 1. We haven't introduced the sample space, but we have talked about the sample space. And so here, let's introduce it now, I guess. S is what we call the sample space, which is the set of all possible outcomes. The set of all possible outcomes. If I flip a coin, my possible outcomes, heads or tails. If I flip a coin, one of those has to happen, and that's why the probability of the sample space is 1. Okay? So if you're considering heads or tails, well, one of those has to happen, then the probability is 1. All right. We'll see it in a bit. But a to the power of c, and there's lots of different notation that we can use. Sometimes we use a prime, but I'll use c, or try to remember, is the complement of a. Yeah, you can kind of dig deep in the term there, the complement of a. Okay, and so if I flip a coin and a is flipping tails, the complement of flipping tails must be heads. Right? So the probability of flipping the complement of tails must be 1 minus the probability of tails. I'm going to just subtract the probability of tails. Another kind of easy complement that we can think of is if I tell you, oh, well, 20% of students don't pass this course, right? Well, now you know the probability of failing is 0.2, but what's the probability of passing? 0.8 or 80, yeah. Why? Because there's only two possible outcomes, pass, fail in this situation, right? It's not as high as 20, don't worry, but I wanted some easy numbers. Right? And so what you do kind of in your head without calling it the complement rule is you take 1, right, minus the probability of the outcome happening, right? And that's the probability of the complement. Okay? So the complement is really just the opposite. Okay? In fact, it's everything in the sample space that's not A. Okay? So if we think about rolling a die, right, the probability of the complement of rolling a 6, okay, anything but a 6. Well, that could be a 1 or a 2 or a 3 or a 4 or a 5, right? Or more simply, 1 minus the probability of rolling a 6. 1 and 6. Okay. So we'll see those again. I just want to introduce them in the order that they appear on our formula sheet for now. What we just talked about is called the addition rule for events A and B. So we've got these generic events A and B. And it says that the probability of A or B, you're able to rephrase a problem as, okay, I want to find the probability of A or B. It's going to be the probability of A plus the probability of B minus the overlap, which is the probability of A and B. So here, we need to subtract the overlap. Which is what we did kind of naturally in the card example. In fact, this is just four numbers, right? And in a question, I can give you any 3 of these components and ask you to solve for the 4th. We'll hold off on the next ones for 2 reasons. I tend to not use this line at all. We'll talk about it, but it's one of those kind of thrown in there to be proper, but then we can just work with the probability of A and B if they're independent. Okay. Notice the difference is or versus and. And then on Thursday, we'll do conditional probabilities. So don't worry about that now. Okay. So from our formula sheet, what we just established is the probability of A or B, which is what we're working with, is the probability of A plus the probability of B minus the probability of A and B. So what's this going to look like in terms of a question? Okay. What's the probability? This example is so fun. What's the probability that a randomly sampled student thinks marijuana should be legalized, or they agree with their parents' political views, which kind of explains what our 2 categorical variables are as well. Okay, so we've got their responses to the legalized marijuana? No and yes. And do they share their parents' politics? No and yes. Right, 2 outcomes each. Huh? And from last day, right, we know how to read this table and pick out some probabilities, right, or proportions. So the hard part, and let's just ignore the options because we'll just do it and then pick our option. The hardest part, I think, is translating this question into something that looks like what's on our formula sheet, right? That's hard. But you have to pick something to be represented by A and something to be represented by B. Now, what's nice is I see this or here. So I'm really latching onto that or. Yeah. So what I'm going to do is I'm going to pick apart the question and call this A. Whether they think marijuana should be legalized. Now that's the positive answer to A, right? Yes. Yes, they think it should be legalized. But let's call this B. Usually we try to attach kind of a descriptive label. Sorry, I gotta sit down in a little faint here. No. And that would be bad if I fainted on this. Not great. Can anybody see me? I don't usually like to sit down because I'm always trying to see everyone. Can't see you. All right. All right. So in terms of the probability of A, which is what we'll need, right? And so here we want to find the probability that a student thinks marijuana should be legalized, which we've kind of just grouped into A, or they agree with their parents' political views, which we've grouped into B. We need the probability of A. And so really what we need is we need the probability of legalize, I'll use the shorthand MJ and yes. And maybe I'll do it down here. So the probability of A is really shorthand for the probability that someone said yes to the legalized marijuana question. Now, how are we going to find that? This is regardless of their parents' political views, right? And so in order to find this probability, what do? Well, I want to be in the yes category here, and I have 114 out of 165 students, right? And that will be our probability. And so here I have 114 out of 165. That takes some practice, but once you kind of get a hang of it, then you're off to the races. Then it's really nice when I give you this contingency table, right? And you have to draw your probabilities from it. And then now we're just doing a little extension using the formula to find additional probabilities. Okay. If B is that they agree with their parents' political views, right, then that would be a yes to the share parents' politics, right? And so what we can do just independently here, probability of B, I like to find the probabilities and then put them into my formula. Right? That's the share politics. Trying to keep it short here. Yes. Now, we don't want to dive into how they felt about the marijuana question. The probability that they share their parents' politics is going to be the 118 out of 165. Huh? There. There's some overlap here, right? Especially if we read it like this. We looked at that 114, and then we looked at this 118. Notice I've crossed that 78 twice, right? Which is the probability of A and B, right? And so the probability of A and B is, do I have to write it out? Yes, I do, I guess. Because it's our first example, really, so I should probably do it properly. But A is legalize marijuana, yes, and share politics, yes. Didn't even have room. From the table, though, right? This would be a standalone question, right? What's the probability of a student wanting to legalize marijuana and they share their parents' politics? Right? You can find that from the table, and that's going to be the 78 out of 165. Right? So we get 78 over 165. Oh. Do I have room to swap these? I'll just do an arrow. Now that we have those components, I'm going to float them up top. I should have done the individual probabilities first and then the full. Oh, well. Float them up top. The probability of A I can replace with 114 out of 165. Probability of B, I can replace it with 118 over 165. And then finally, minus 78 over 165. Which is my calculator. My trusty calculator. Luckily, they have the same denominator. And maybe it's one of these. Oh, looks pretty good. How about B? We'll just calculate it for good measure. I get 154 out of 165. Ugh, cramped. It is tempting to convert these fractions into decimals, and you are allowed to, right? But if you're rounding too soon, then you might lose some values, and your answer might be slightly off. That's more of a problem with the online homework system, right? Because it might say, it's a little off, right? But you are allowed to use decimals if you prefer. Or you can dust off your fraction skills. we always have common denominators, so don't worry about it. Yeah.
So for answer, what did you get?
Oh, I got 154 over 165. I snuck it in here.
If you rounded that, what would that be?
So that as a fraction, 165, I get 0.933333333. Repeat. Cool. Cool. Okay. So what we just introduced, but I already kind of sneak previewed it, is called the general addition rule. Now, what's nice is the special case. We don't really need to know the special case, but the special case is if A and B are disjoint, right? If they can never happen at the same time, then what's the probability of A and B? Right? Be 0, right? They can never happen at the same time. The probability is 0, right? And so here, if A and B are disjoint, they can never happen at the same time. So the probability of A and B is 0. It just simplifies your formula, right? But I would consider that just a special case. And I know it's in the note here, but sometimes if I just write it special, then it sinks in better. So then you have a special case, but I want you to use this general addition rule, which is why it's the only one I give you on the formula sheet. And then understand that if they're disjoint, then the probability of A and B is 0, right? That's more valuable. Often I'll give you probabilities as a probability distribution. Right? And so, because sometimes the probabilities are not evenly distributed, like we've seen, and I guess we'll continue to see, sometimes they're kind of unevenly distributed. So how we communicate the probabilities of different events is often through a probability distribution. Now, what a probability distribution does is it lists all the possible events and the probabilities with which they occur. Usually, the events go up top, and the probabilities, the corresponding probabilities, go below, usually. There are some rules for probability distributions, right? And often on test 1, I'll have a question asking, is this a valid probability distribution? And so that means you have to check these 3 things, right? And if they're satisfied, it's a valid probability distribution. And so here, I'll clarify to see if probability distribution is valid. We check these. First thing, the events listed must be disjoint, right? There can't be any overlap in our probability distribution. So if we have this example, and I always think it's kind of funny to use the word kid, but anyways, the probability distribution for the gender of 1 kid, which then a kid is also the name of a baby goat, which makes the example even cuter. So you can think of a baby goat. the probability distribution for the gender of one kid, well, still male. It still works. That's why it's so cute. 0.5 and 0.5, let's say. Okay. And here, right, we'll assume that these genders are disjoint. They can't happen at the same time. Yes, I know. The second rule is, well, it just stems from rules of probabilities, really, right? And so each probability down here must be between 0 and 1, right? But that's true for any probability, right? And so you're really just going through the rules of probabilities, which is why I like the question. 0.5 is between 0 and 1, and 0.5 is between 0 and 1. Great. And the probabilities must total 1, right? And so here, this is what we call, this would be the sample space. And the total probability must be 1. Right? If I've listed all the possible outcomes, right? It lists all possible events. Maybe I'll highlight that. Well, that's going to be the sample space, right? And the probabilities, which still have to follow just general rules of probabilities, right? Which means that they have to be between 0 and 1, and they have to add to 1. Right? Okay. We can even consider the probability distribution for the genders of 2 kids, 2 baby goats. We can have male, male, female, female. And, right, if we think about these baby goats aren't born at the exact same time, probably year 1, year 2, that kind of thing. And so then order matters, right? And so a male, then a female would be different from a female, then a male. In terms of the probabilities, though, they end up being the same. Okay. And they're just a quarter across the board. But we also see that, okay, this is still a valid probability distribution. All these possible outcomes, right? We have more because now we have 2 kids, right? And so now we have 4 possible outcomes, right? But we've listed all of them and they're all disjoint. That's cool. Each probability is between 0 and 1. Great. So far, so good. And if we add these all up, we get to 1. Right? So it is a valid probability distribution. Okay. Had more. I'm going to hold off. Decisions. In a survey, 52% of respondents said that they are Democrats. What's the probability that a randomly selected respondent from this sample is a Republican? Now, this is a trick question because we're thinking about the states and they really only have 2 parties, but we do need to remember that people are allowed to run as independents, right? They don't tend to be elected as presidents, but maybe one day, I don't know. And so you just have to be careful about all the possible outcomes, right? And so, yes, of course, we have these 2 prominent parties, right? Democrats, Republicans, right? But there are independents as well. Okay? And so just want to be careful, right? What's the probability that a randomly selected respondent from this sample is a Republican? I'm going to axe this first one, right? And I'll make a note, right? Consider independents. Consider those running as independent. I'm sure that's not the terminology, but right? Because 0.48 is kind of our gut reaction, right? If 52% are Democrats, then I can take the complement, right? Which we did a sneak preview of as well, right? Kind of leading up to that, of course. So then 1 minus 0.52 is 0.48. And so that's why you might have jumped at the 0.48, but you have to consider all the possible outcomes. It's not more than 0.48, right? Because again, what about those independents? They're going to take a little chunk. I'm okay with saying I would feel comfortable saying less than 0.48. I would even say less than or equal to 0.48. Right? If there were no independents that year or whatever's going on, right? That's a possibility. But I would say less than or equal to, right, allowing for the equality, but not forcing it, right? Then I would say I'm okay with C. Right? Or I could be convinced of D because it doesn't tell us how many parties there are and things like that. But I'd be happy with C. So we already saw a sneak preview. We kind of felt the previous question leading us into the complements, right? And here we are. So the sample space, here it is introduced formally. The sample space is the collection of all possible outcomes of a trial. A couple has one kid, so I guess it was children and not baby goats. Too bad. Anyways, maybe a couple of goats has one baby goat. What is the sample space for the gender of this baby goat? We're going to use capital S to denote the sample space. I'll write that here. Denoted by a capital S. You have it on your formula sheet too. And so what we can do, and it's not terribly important that you use set notation, but technically a set is wrapped up in curly brackets. And then we list the possible outcomes inside. And so the sample space is going to be, let's say, male, female. And we saw those in the probability distributions as well, right? We said, well, actually, when I list the possible outcomes up at the top in our probability distribution, that is my sample space, right? So you list your sample space. So we've already seen these. A couple has 2 kids. A couple of goats has 2 baby goats. What's the sample space for the gender of these kids? And so just kind of getting familiar with the notation, S is going to be, and I'll do the same setup as they had, male, male, right? Female, female, male, female versus female, male, which would be a different combination, right? Complementary events are 2 mutually exclusive events. And we were calling these disjoint. But like I said, we need to be kind of flexible on moving between the two. And because mutually exclusive is a well, it's not a term, a phrase that we use in regular language, right? That's nice to use as a link to the disjoint. But complementary events are two mutually exclusive events or disjoint events whose probabilities add up to 1. There's a little extra that in there. So, for example, if we're told that a couple has 1 kid, 1 child, 1 baby goat, if we know that the baby goat is not a boy or male, what is the gender? Well, just knowing that it's not male tells me that it's female, right? Because these are complementary events. Whereas if we think about if we have 2 kids, right? Think about our sample space. If we know that they're not both girls, right? So we know that they're not both females. Right? What are the possible gender combinations for these kids? Well, it could be male, 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 female, female, male. Right? So if you list all the possible outcomes, and then you can remove the one that you don't want, and then you have a list of the complementary events. And maybe I'll say this is the complementary event of female, female. Right? You just remove it. Remember, disjoint is these 2 things, these 2 events cannot happen at the same time. Now, that's talking about the events. Now, I want to talk about independence. Kind of hinted at the beginning, right? Flipping a coin is independent. What does it mean to be independent? So 2 processes are independent if knowing the outcome of one provides no useful information about the outcome of the other. So independence is about the probability. And the probability of an outcome is not influenced by what's happened in the past, right? Flipping a coin, flip a coin again, you flip a coin again, they're all independent and the probability never changes. The probability doesn't change. And so independence involves the probability, whereas disjoint involves the events, right? These events can never happen at the same time. Okay. So I just want to clarify that because that can be really tricky. Involves the events, right? So now we're talking about independence. If knowing the outcome of one provides no useful information about the outcome of the other. There are many non-independent events, right? But just like disjoint, we start here and it'll become a special case. But it's a nice place to start. So knowing that the coin landed on a head on the first toss, it doesn't give me any information about the next toss. So outcomes of 2 tosses of a coin are independent. Right? And that's why we say the probability just stays 0.5, 0.5, 0.5. Whereas if you know, so you've got a deck of cards, you're playing cards with your friends, and you know that the first card drawn from a deck is an ace. Okay? Now, assuming you're not replacing these cards, right? Most card games, you deal them and they're out, right? So you know what's happening in the rest of the deck, right? So now, knowing that an ace has already been drawn, that does provide useful information for determining the probability of drawing an ace in the second draw. Right? So that means that the outcomes of two draws from a deck of cards, right, are dependent, not independent. And so, for example, we can find those probabilities if we think about it a little bit. The probability of an ace on the first draw probability of an ace on the first draw, there are 4 aces, 4 and 52. So already kind of a low probability, but it's there. Probability of an ace on the first or on the second draw after that first draw. And so probability of an ace on the second draw, knowing an ace was drawn, this is going to be lengthy, was drawn on the first draw, is going to be what? So if you know that an ace was drawn on the first draw, there's only 3 aces left, right? But there's also only 51 cards left, right? So then we need to adjust the denominator as well, right? I think the 3, so going from 4 to 3 is relatively intuitive, right? But it's the, okay, but then my total deck is now not 52 because an ace is out there already, right? Assuming without replacement. So now my total is 51. That's the part that kind of trips people up. Okay, I've got more to say about this one. Just a second here. I need some lines. I've decided. I'll just move this down. Hey, it's pretty good. If I give myself some room here. What if I call this A and I call this whole bunch of words, so ace, an ace drawn on the second draw, knowing an ace was drawn on the first draw. I'll replace that with shorthand B. Ah, I know. Then, in this scenario, I want you to find the probability of drawing 2 consecutive aces without replacement. Probability of drawing 2 consecutive right? One after the other. Aces. And I'll clarify without replacement. Without replacement. Which is really saying, okay, you got an ace on your first draw, and then you got an ace on the second draw, knowing that you got an ace on the first draw. So how I like to solve these problems is I call them slots because that's kind of a fun way to think of them. Yeah. But really what I want to do is I have these kind of empty slots, right? And here, event A happened, that's an ace on the first draw, kind of makes sense. B, not so much, right? But B had to happen as well, right? Drawing an ace on the second draw, knowing that I had an ace on the first draw, right? So if I want these two things, right? So drawing two consecutive aces, that's going to translate to A and B. And just like the or translates to addition, and is going to translate to multiplication. And so here, and means multiplication. So if I want to find the probability of A and B, right, which would be an ace on the first draw and an ace on the second draw, knowing that an ace was drawn on the first draw, right? That's the problem that I'm trying to solve. What I'm going to do is I can have the probability of A here and the probability of B, and I can multiply these to find the probability of A and B. So here, this becomes the probability of A times the probability of B. What's one thing to be aware of? How I found this second probability, this is called a conditional probability, which is what we'll deal with on Thursday, so it felt like close enough. We'll introduce it here, but we'll talk more about it on Thursday. But really what we have is the probability of an ace on the second draw given, right, but knowing, given that an ace was drawn on the first draw, right? That will be, so the probability of an ace on the second draw, well, that depends, right? So it's dependent on whether an ace was drawn on the first draw or not. And so to solve this, what we're going to do is you have your probabilities, and usually I just have it like this, A times B, 4/52. And if you want to use decimals, you can, times 3/51. There's a reason I'm introducing this now, because on your assignment, and you'll know what I mean when you see it, there's a sock problem. And you'll think, oh, the sock problem, she talked about this. And so you've got a drawer of socks, and for some reason they're not paired up. It's weird. But you're just drawing blindly. And you've got maybe green socks, red socks, black socks, white socks, whatever. So you have some probability of each color of the sock, right? And so your first sock, let's say you have 12 socks, right? then some number of them will be red, for example. And then, but the following sock, you've already pulled one of the socks out. So you're allowed to assume that it's happening consecutively. That's usually a tricky problem. So that's why I wanted to bring it up here. But it also gives you a way to solve these probability problems just using the slots. Most of these problems you can solve with slots. And so now I think we're ready for the next example. I think so. Oh, that's what I was going to say. If A and B are independent, right, then we wouldn't need to make an adjustment here, right? And so let's see here. What if we did another, that's what I wanted to throw in here. What if I wanted to find the probability of some independent events? Find the probability of rolling 3 2s in a row. A die. Kind of implied, yeah.
Six-sided?
Yes. All our dies are six-sided. I know. None of those crazy other dies. I'll say six-sided. What's the, I think there's like a 24-sided die? Is that the one? 20. It's in the 20s though. I know. Last is 20-sided? Yeah. Okay. Last term when I taught this, one of my students actually had one with her, a 20-sided die. She's like, here's a 20-sided die. I don't think I've ever seen one. So, gonna grab her 20-sided die. If you have to roll 3 2s in a row, or really any sort of consecutive events, right? What you can do is you can set up your slots, as I call them, right? So your first slot is your first roll, right? And so I roll a 2, and I roll another 2, and I roll another 2. Notice how you're saying and in between, and a 2, and a 2, right? And so here, this is the outcome. I like to do the outcome below, and then the probability above, as opposed to a probability distribution, I suppose, but they're different. So the probability of rolling a 2 is 1 in 6. When I see and, I multiply, right? Or when I think and, I multiply. Well, another 2, 1 in 6. 1 and 2, another roll of 2 of a die. If you think about this, this will be the same probability as any combination of 3 numbers, right? Of rolling a die. A 6-sided die is going to be 1 in 6 times 1 in 6 times 1 in 6, right? Which is going to be 1 in 6 times 6 times 6. 1 in 216. Which means there are 216 possible outcomes if I roll a die 3 times, right? And a 2 and a 2 and a 2 is just one of those. Right? But technically, that's any combination out of those 216, right? A 1 and a 2 and a 3, a 3 and a 6 and a 4. Wow, crazy. But all those probabilities stay the same, right? So sometimes we have to adjust the probability. That's what we'll call conditional probability, but the slots still work. Okay? Or if we have independent events, probabilities just keep staying the same. How am I doing? Okay, pretty good. Can I just do a quick blah 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 preview? Okay. Then I want to skip to the next slide. I'll highlight the answer, but I think we'll talk more about. Let's read it quickly, I guess. I know. I can't handle it. Okay, so Survey USA interviewed a random sample of 500 North Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime or makes society more dangerous. Feels like a leading question to me, so that's kind of bad. But anyways, I don't know how else you'd ask it. 58% of all respondents said it protects citizens. But then if we break it down, we are told that 67% of white respondents said that it protects citizens, 28% of Black respondents, and 64% of the Hispanic respondents shared this view, right? So overall, it was 58%, but within the groups, right, we have very different views, right? And so which of the below is true? Opinion on gun ownership and race ethnicity are most likely probably not complementary because there's overlap. Not mutually exclusive. They're not independent. Why? If they were independent, I would expect each of these individual groups to be hovering around 58%, right? But because they're quite different, right? So we've got this baseline of 58%, but then we had kind of 67%, we had a 28%, and then we had a 64%, right? Those are quite different. Yeah? And so our gut reaction is probably that, well, how people feel about gun ownership might depend on their race, ethnicity. Later in the term, we'll have a way to determine if there's evidence for or against it. But for now, we're just developing the idea. And so I would suspect that they're dependent just because they're so different. Here, this 67% of white respondents, we can translate as the probability that said, how do I shorthand this? I don't think I can. So I won't, sorry. Just because they do it on the next slide, so I'll just skip to that. So independence, we said, is all right. If knowing the outcome of one event, right, impacts the probability of the next event, right, knowing that I've drawn an ace, right, that impacts the probability of drawing another ace, for example, right? Or any other card. There's fewer cards. But if the probability that A occurs, given that B is true, so knowing that B has happened, the key word here is this given. This is what makes it a conditional probability. And this vertical line, you read it as given. So the shorthand of, oh, where's my pointer? Of the probability that A occurs given that B has already happened or B is true, the shorthand looks like this: the probability of A given B. Now, if A doesn't care about B, then it's independent, which means that it's just going to be the probability of A. Which means that A and B are independent. The probability that someone thinks it protects citizens, North Carolina, I think in 2013, it was quite a while ago. But anyways, the overall probability was 0.58. This is why I started translating it into shorthand and then I gave up. The probability that a randomly selected North Carolina resident says gun ownership protects citizens given that the resident is white. So knowing that they're white, right, that impacts the probability of how they feel about gun ownership. So how we can shorthand that is the probability that they think it protects citizens given that they're white, we were told was 0.67. So here we have these conditional probabilities. And so here, these are what we call conditional probabilities. The probability that it protects citizens just in general, right, varies by race, ethnicity, and so therefore opinion on gun ownership and race, ethnicity are most likely dependent. Right? If you suspect that they're dependent, right, then the next step is to conduct a hypothesis test. We haven't seen hypothesis tests, but you'll be sick of them by the end of the term. So we're getting there. It's my favorite part of the course. Luckily, it's the whole second half of the course, so that's lucky for me. And so then we'll be able to do a formal hypothesis test in order to determine if they are dependent or not. If the observed difference between the conditional probabilities is large, right, then there's stronger evidence that the difference is real, right? Just like we saw up here, I personally feel like the difference between 67 and 28 is too large to just have happened by random chance. Well, there's a little bit more to that. If a sample is large, right, then even a small difference can provide strong evidence of a true difference between these two groups. Right? So it really depends on the sample size. So we saw the probability that it protects citizens given that they were white was 0.67, which is relatively close to the probability of it protects citizens given that they're Hispanic, which was 0.64. So the difference between 0.67 and 0.64 is, I don't know, kind of up for interpretation. They are different, but they're relatively the same, especially considering the 28%, right? And so under which condition would you be more convinced of a real difference between the proportions of whites and Hispanics who think gun widespread, probably not gun widespread gun ownership protects citizens. At 500, okay, maybe, but I would be really convinced if they were talking about a sample of 50,000 and then they landed on these two proportions or percentages, then I would be convinced that there is a difference there. I know, but we need to do this. We've actually already done the product rule for independent events with my slots. Sort of. How are these my slots? The product rule, so product is multiplication. Okay. The product rule for independent events says that the probability of A and B, so notice here I have an and, is going to be the probability of A, time, hey, where's my pointer? The probability of A times the probability of B. And if you wanted to extend it to any number of events, right, toss a coin 10 times, right? You make 10 slots. Really, what are you doing? You're making slots for these probabilities to be multiplied, right? So you can list the event that has to happen below and the probability that it happens with above, and then multiply through. And that's how you're going to find all these and probabilities. For independent events. If you toss a coin twice, what's the probability of getting two tails in a row? Well, we can use my slots. I get tails, and I get tails. Probability of tails is 0.5, and the probability of tails is 0.5. I get 0.5 times 0.5, 0.25. Or you can use the fractions like they have. And I know, okay. It was an ambitious attempt today, but we'll pick up here on Thursday. If you have any questions, let me know. But give these next few examples a try. See you on Thursday.